Hi, chemistry students. Trying to make a quick video on the atomic orbitals. So, what we are looking at is our current model of the atom, and we should feel comfortable with this. Protons and neutrons in the nucleus, electrons orbiting around in some type of a cloud or some type of a shell. We've left it pretty vague up until this point. So, in our next unit, we are looking at the electrons. All right, so you may have seen stuff like this before when you studied atoms in maybe middle school or integrated science. You might have looked at these shells. So here, for example, is potassium. It has 19 electrons. You might remember 2 electrons in the first shell, 8 in the second shell, 8 in the third shell. Right, that gets us to 18. So that 19th electron would be in the fourth shell. You may have seen this, and it's not 100% wrong, but it is certainly not 100% accurate either. So we're trying to have a better model here. So here's just kind of a rundown of our models of the atom. John Dalton gave us this billiard ball model, and those were just solid balls. That's how he viewed the atom. He was incorrect. Then J.J. Thomson did the cathode ray experiment. He identified the electron, and he came up with the plum pudding model. Now, we think of this more as like a chocolate chip cookie. The negative electrons are like the chips, and the cookie itself is positive, right? But Thomson's saying, hey, there are subatomic particles, protons and electrons. Rutherford comes up with the idea that we have a nucleus. And so the nucleus is where all the mass is going to be, the protons and neutrons, and the electrons. He just draws this symbol. All right, now Bohr, he's going to come up with the planetary model. So he's going to think of the electrons as orbiting the nucleus like planets orbiting the sun. And what Bohr will do, he'll actually come up with a really good estimate of the distance the electrons are from the nucleus. But they don't orbit in neat paths. So our most current and our most accurate model of the atom is the quantum mechanical model. So that's what we are studying, the quantum mechanical model of the atom. Now, the the hook to quantum mechanics is that the electrons behave as waves, which is really weird. So if the waves go around in a circle, we see how we get certain areas where they don't exist. Those are the dots, and certain areas where they exist at really high peaks, right? So waves, they come up and down, and they can interfere with one another. So we're going to get some really funky shapes as we go through this lesson. And this is the type of information that the chemists have used. So this is pretty intimidating. And it uses these letters N1 through N, L, and M, and those are called quantum numbers. And we don't have to worry about that right now. But those numbers explain the shapes of these electron orbitals. The quantum numbers come from this incredibly scary math equation that we are not solving. I can't solve this right now. It's got some really funky, complicated math I have not seen since college. So what are we learning? We're learning about orbitals. All right, the electron's not in neat fixed orbits like Bohr proposed, but an orbital is a 3D region around the nucleus that indicates the probable location of an electron. All right, where will that electron be 90% of the time? All right, we can't think of 100% for the electron because the electron moves too fast. It teleports. It does all this weird thing, quantum entanglement, all kinds of fun stuff, quantum tunneling. Anyway, 90% of the time we can get an idea of where the electron is. We can do that. All right, these are going to be our orbitals. So think about you. You're at home. You're watching this video. You're learning. Where are you 90% of your school day? You're probably at home. Maybe sometimes you step out. Maybe you're doing school on your phone. Who knows? But the idea is I have an idea of where you are most of the time. All right. This is what some of the images of these orbitals look like. All right. Scientists came up with orbitals by studying the light that electrons produce. So there's 4 types of orbitals. The first type is called the s orbital, and it is a sphere shape. All right. And it holds 2 electrons. Right. So I like to think of it as like a 2-seater car. 2 electrons can fit in an s orbital. We're going to see multiple different types of orbitals, and we're going to get different sizes of them. S orbital, sphere, holds 2 electrons. The second orbital is the p orbital, and scientists call this the dumbbell. Now, I always think, if that's a dumbbell, how often are these scientists really working out? But it has 3 different orientations along the x-axis, the y-axis, and the z-axis. So each orientation holds 2 electrons. That gives us a total of 6 electrons. So 6 electrons can fill in the p orbital, and those 3 dumbbells overlap and they kind of make this jack shape. All right, now the third type of orbital is the d orbital. It looks like a 4-leaf clover. And these shapes, right, these shapes are the locations where an electron could be. All right, the electron essentially sweeps out those shapes. Imagine looking at like a ceiling fan. When the ceiling fan's on, you don't know, it looks like it's solid, right? The blades in all those spots. Well, the electron, it's moving, but not in a circular pattern, in a wave pattern, so it's making these shapes. All right, there's 4 4-leaf clovers, and then there's a dumbbell with a donut around it. It's kind of a weird little shape. Each orbital holds up to 2 electrons. So that gives us 10 total electrons in the d orbital. All right, so that's like a 10-seater car. That'd be like a minibus, right? It has a lot of space for electrons to exist in. And our last, and this is what it looks like when they all overlap. It starts to get really funky. Our last type of orbital is the f orbital, and it has 7 different orientations, 2 electrons in each. Again, this is the movement of the electrons in a wave pattern. And I'm not even going to try to give this shape a name. I'm just going to call it crazy. All right, you have to say crazy. If you say cray, that's not good enough. You'll get partial credit. You have to write crazy, the whole thing. But again, 2 electrons per each, so that gives us 14 total electrons that can fit in the f orbital. All right, so that's space where electrons can exist. So again, 4 types: S, P, D, and F. Their orientations grow by 2, so we go from 1 orientation to 3 to 5 to 7. So that means 2 electrons in S, 6 electrons in P, 10 electrons in D, 14 electrons in F. And they begin to overlap. So we can get these orbitals at different energy levels, we're going to say. So think about like those shells. We can have multiple, instead of shells, we can have multiple orbitals at different energy levels. We can get 1 sphere, then 2 spheres, then 3 spheres. It's kind of like those nesting dolls. It's the exact same shape of the orbital, it's just bigger. All right, and the same thing happens for the p orbitals and the d and the f orbitals. And when they begin to overlap, this is an s overlapped with the 3 p's, we get this funky looking shape down here. Now, this is a total of 8 electrons, 2 from the s orbital and 6 from the p orbital. So 8 total electrons. And I think it kind of looks like an everlasting gobstopper from the Willy Wonka movie. All right. Anyway, it is a sphere with the dumbbells. They overlap each other. These are spaces where the electrons can exist. So in the first ring or shell, there's an s orbital, 2 electrons. In the second shell, there's actually 2 types of orbitals, s and p. And then we get spd, then we get spd and f. And these are all spaces for electrons to exist in. All right, so we get overlapping of these atoms. So this is what a scandium atom would look like, and this is element number 21. So it has 21 electrons. Its first 2 electrons would be in the first energy level s orbital. All right, the next 2 would be in the second energy level. So it's a bigger orbital, but it's also an s, so it's a sphere. They're overlapping like those dolls. Now we have the 2 p's, and they're in the different orientations. So that's along the x-axis. All right, and then the y-axis is going to overlap it. All right, so we can see in this model it coming in, and then we're going to get the z-axis, and they all overlap. So now we have 1s, which is 2 electrons, 2s, which is 2 electrons, and 2p, which is 6. Now we're at 3s. It is a bigger sphere, and it's overlapping that entire gobstopper in the middle. Now we have the 3p. Again, we're going in the x-axis first. All right, so 2 electrons fit in that dumbbell. 2 more electrons are there in the 2py, and we're going to get 2 more electrons in the 2p along the z-axis. Okay, so now after 3p, oddly, we're going to go to 4s. We're going to get a much bigger sphere, and it's going to overlap that entire thing. Think of those nesting dolls. It's overlapping all of that. And now we're going to start to see those d orbitals. So 20 electrons are present. That last electron, it could be in that shape. All right, it could be in this 4-leaf clover. All right, so we get all of these different axes. They overlap each other. The whole point is the atom just looks like this blob. There is all of this wave interference happening. It's kind of circular, right? It does kind of look like a sphere, but it's a little lumpy. All right, so that's a good word to think. It's a little lumpy, and we're going to be able to tell where the electrons are for any atom because they always fill up those orbitals in the same pattern. So we'll see that pattern in our next video. But this is what an atom looks like. It's not quite a neat sphere. It's not that planetary model. This is the quantum mechanical model.